But this condition in the array, Euler characteristics times entropy is constant in this array. So you can restrict to this part. You have one-dimensional graph, and you can recover entropy function of this using this times and the Euler characteristic of this, and you can get the information over here. So we only want to compute in the face the entropy function on the this face of the Thurston polytope. So that's very good, because we have three-dimensional picture, and if we want to compute entropy, we have to draw the four-dimensional picture. But if we restrict to this two-dimensional part, we can draw the picture. And so let me that is a picture of entropy function on the delta. Here is a delta. The original delta is diamond, but I changed some coordinate and it's right square. But here is a delta, and we can compute the entropy function. And let me see. So how to compute the entropy is Fried and Otto have also it's very strong theorem. For any 2 point sigma and tau in the cone of the fiber surface, sigma from sigma we have some surface boundary, and in there invariant lamination of the pseudo-Anosovs map, and so we have invariant lamination in the, let me see. So for sigma, we have invariant foliation in here and also in here. But so they are invariant. We suspend this foliation for the interval direction, and we get the two-dimensional foliation on the magic manifold using sigma. And also, there are other surfaces defined by tau, and there are another invariant foliation here, and so there are another invariant suspended lamination here. But the theorem says if this 2 point is on the same fiber face, sorry, it's not surface but face, same face of the Thurston polygon, they are isotopic in the magic manifold. So essentially, there are only one lamination in the magic manifold correspond to the face of the Thurston polygon. And using this theorem and Otto's recipe, we can compute this polynomial for the sigma. The dilatation lambda of this homology class is just the maximal, just the largest real root of the following polynomial. And if you see very carefully this polynomial, it has only one real root greater than 1. And so let me see. How to compute this polynomial is hard to explain, but the answer function is like this. And let me see. Okay, I won't explain how to compute the polynomial, but using some kind of things. So first we want this suspended foliation in M. So we have changed this manifold in the link complement of this is link. This link and this link is the same link. You can change by isotropy, but you can cut along this blue disk and twist once you get this link from this link. And so this and this different link, but these two have same complement. And this is a surface bundle like this. And we want to write this alpha and beta and gamma in here, and it's a complicated picture. And then we want to know the invariant foliation. And so using blade, from this, we change this here sigma inverse and sigma to, let me see, here sigma 2 and sigma 1 inverse and sigma 2, and this foliation goes to this by this map. And this is some representation of the suspended foliation. And then, then it's very complicated, but we want to compute some invariant measure. So we make some weights on every part of this graph, and we follow the way which weight goes to where, and we have some equation like this. And we want to know there is some invariant measure means this equation have some solution, and we need determinant of this part equal to 0, and we have this equation. And I think I don't explain almost anything, but such kind of things give us this polynomial. And the only theoretical reason is here. If you have two points, the suspended invariant foliation is same. And in other words, if you have this foliation, you can get every other invariant foliation in the surface from the original suspended lamination. And so we can compute this polynomial. And let me see how many time I have. 10 minutes. And okay, so this is an entropy function delta, and so the next thing is how to compute the entropy after den filling. And but it's very easy. So for example, in this case, complement of this link is a magic 3 manifold, and it has a surface bundle like this, 4 punctual disk surface bundle. And if you forget this blue component, we have another manifold, which is a den filling of this manifold. But we want to know the filling coefficient from the original picture. So from here to here, we using 1/0. But from this picture, we have to use the coefficient minus half, because from here to here, we twist once along this blue disk. And but we have from here to here some den filling. We have new surface, new field surface, and we can compute the entropy in here and here. And どっちだOkay. Usually the entropy doesn't change. So the entropy of before filling and entropy after filling is almost always equal, and except when the invariant foliation have one prong in the field puncture, I say nothing about this. But in that case, entropy goes down after filling. And when it happens is the filling coefficient is in Z, or sometimes in -2 minus 1 over n, and it's very rare in all coefficients. And so there are very rare cases. We can't say the exact entropy, but in other case, entropy doesn't change from original entropy. And then we want to know the Thurston polytope of after surgery manifold. And in this case, we have magic manifold has three-dimensional second homology. And so this after surgery we have two-dimensional second homology. And this point 1, 1 is correspond to here because this surface and filling this we can get this. These 2 points correspond to this point and this point. And this surface is correspond to this surface. So we wonder around here is corresponds to fair, but it's easy to determine because this type of surface is let me see this boundary slope is just the surgery slope. And we can get from here to here. So we want to know what surface have the boundary slope is equal to the surgery slope. And it's easy to compute because the slope is this. And so if we fill first component, the surgery coefficient PQ is just P over Q is equal to A over B plus C. And so P is just GCD分A plus B, and Q is just GCD分C. And so we have this equation. And so the second homology of the then filling is correspond to the linear slice of the original Thurston polytope. And also we can compute the Thurston norm of here using the Thurston norm of here. And let me see. Okay, I have 6 minutes, and I want to show you some toy. Okay, this is a Thurston polytope of this gray one is Thurston polytope of magic 3 manifold. And let me see. This なんだっけ。Okay, if you slice, you do some then filling on the magic 3 manifold, you have some linear plane correspond to the then filled manifold, second homology of then filled manifold. In this case, I do 2/1 surgery, and we have this plane as a the second homology of the filling manifold. And so the intersection is blue line, but we can compute the Thurston norm is different from original one. The new Thurston polygon in the Dehn filling manifold is this green one. So for every Dehn filling coefficient, we can compute the this green one is the Thurston polytope of the Dehn field manifold. And so we should back to here. So let me see. Okay. So finally, we have everything. And so our experiment is like this. Let sigma is x alpha plus y beta plus z gamma, and xy moves to 0 to 100, and z goes to minus 100 to maximal of x or y. And we need z coupling. So first we compute all the boundary slopes. Then we can find the Dehn filling of this hyperbolic or not using of the Martelli and Petronio's theorem, which determines all exceptional surgery of magic 3 manifold. And so if this Dehn filling is hyperbolic, we can compute the Euler characteristic and entropy, and also the topology of the fiber surface. So the example is like this. Let sigma be 2 alpha plus 2 beta plus gamma, and so it has boundary slope like this. So there are many, usually 8 possibility of Dehn filling, but these two are equal. We have this and this and this and this and this. And Petronio and Martelli said that these 4 are hyperbolic, and this one is not hyperbolic. And for this 4 manifold, we can compute the entropy and entropy times Euler characteristic, and that is sigma 1, 1, and the minimal entropy is 2 over 3 plus root 5. And we compute such things for every element in between 0 to 100. And so then we have this is a table, and yeah, if we print in paper, you can't see, but digital is very good because we can't like this too much. What is this table is? Let me see. Among that 100 times 100 times 100 homology class, the minimal dilatation among that 100 times 100 times with genus with this, with puncture with this. So first notice that 0 puncture sphere or 1 punctured 2 or 2 punctured 3 punctured sphere or no punctured torus have no hyperbolic surface boundary. So there are nothing. And for 4 punctured surface, the minimal among our experiment is surface boundary corresponds to 1, 0, and with 1 component surgery by this minus half coefficient. And you can see in this direction. So first, we can see around the top line correspond to the punctured spheres, and you can see it always last coefficient is 0. And let me see, it have 50 row and 50 columns, and maybe you can see these two are very similar, almost half of the number of puncture. And in the second row is a punctual torus. You can see all of the surgery coefficient is 1. It corresponds to Whitehead ring complement. And in other direction, we think this part, closed surface case, it's hard to see, but maybe around there, you can always have minus half or minus 3/2 in the surgery coefficient in everywhere. And sometimes there are -4, but -4 surgery of the magic 3 manifold and minus 3/2 surgery of magic 3 manifold is isometric. This is a different description of the same manifold. And so we have this big table and some observation like this. Okay, sorry. Maybe I have two. Shall I have 2 more minutes? For example, for this punctured sphere case and punctured torus case and closed surface case, we have some observation. And the other observation for genus is smaller than the number of puncture. But and maybe I can finish here, but we have some theorem to justify this observation, like for this, for the punctured sphere, and for the closed surface bundle, the Hironaka's result is using the -1/2 surgery of the magic 3 manifold, and we have better bounds using -3/2 surgery of magic 3 manifold. And our conjecture is if the mapping torus is isomorphic to the magic 3 manifold or Dehn filling, Hironaka's bound and our bound is best possible. There are no other good entropy, small entropy comes from magic 3 manifold. And maybe this conjecture is true, but we can extend our conjecture to without any condition, without this, the complement is Dehn filling of magic manifold. We may omit this condition, and our conjecture is without any condition, our series attains a minimal entropy. And finally, I have to show this picture. This picture is entropy function after filling every component. And so you can see around let me see, it's very hard to see, but sorry. That graph, this graph is the entropy function of the filled magic manifold, and just wait maybe a few seconds. The very lower part is like this, and around here is discrete. And there are only finitely many accumulating points, and if you see from above, you can see just this picture, and the accumulating point is around here and here and here, and they correspond to -1/2 surgery and minus 3 over 2 surgery. So if we search all minus 1 half surgery and minus 3 surgery, we may get all small dilatation from the magic 3 manifold. And that is a reason of the first conjecture. So we have every small entropy from magic 3 manifold by our series. And okay, second conjecture is from this. This is a very strong theorem. And further, Lenin and Margaret said that there is only finite remain 3 manifold, and the all pseudo-Anosovs whose entropy less than some constant lives in one of the den filling over here. So especially for all minimal entropy leaves only finite remaining 3 manifold. So and the magic manifold, in the magic manifold there are 5 minimal entropy leaves. So we can expect other minimal entropy may live in magic 3 manifold. That is evidence for our second conjecture. Okay, I'm sorry it's too long. Thank you very much.